Hello, this video is one of a series of videos each describing one logic board within the Qibec 1-bit 1 instruction transistor CPU that you can see right here. And today we'll be talking about the 8-bit latch that you can see right here. Within the CPU it is located here, here, here and here. It occurs 4 times and it is used to implement the address latch. It is a 16-bit double address latch, so you will need 4 8-bit boards. If you look a bit more closely at this board, well, the name says 8-bit latch, and it is implemented using the same subcircuit 8 times, as you can see, 1 time for each bit. So each row is a duplicated subcircuit. Each cell within each row is a logic gate. And if you look closely, you see that within each cell, each logic gate consists of 2 transistors and a number of resistors. It is not very important for now, it will be discussed in another video. If you look at the inputs of this board, you will see the positive and a negative input, the VCC and the ground. It has a low active reset input, an enable input, and for each bit it has a data input labeled A, so 0A until 7A, and for each bit it has an output labeled Y, so there's 0Y until 7Y, as you can see. It's basically the same subcircuit 8 times. In this video let's talk a bit about how this block, let's talk a bit how a 1-bit latch, what it looks like from the outside, then how it can be built up from simpler logic blocks and logic gates, and finally let's see how it works, both on the whiteboard and on the breadboard. So, if you consider an 8-bit latch consists of 8 1-bit latches. So let's look at a 1-bit latch, because if you understand that, then the 8-bit latch is obvious. 1-bit latch in this case looks like this. It has an input D for data. It is a 1-bit input. It has an input E for enable, to enable the latch. And it has an output Q. Furthermore, it has a low active reset input. A reset input resets the output to 0. Now, in terms of functionality, you can look up on Wikipedia, for example, how this block works, except in short, the input D is copied to the output Q if and as long as input E is activated. In other words, if input E is activated, the latch is transparent. Whatever change occurs in the input occurs at the output. When E is no longer activated, the output Q stays put. In other words, the output Q will remember the state that D had at the moment E was inactivated. We'll see, this makes more sense when you see it on the breadboard. Reset input can always be used to force the output to 0. Let's assume 0 is the idle state of this block. Okay, now let's draw this somewhere in a corner. So while we construct this block out of simpler blocks, we can still see what it should look like. There we go. Now in a previous video we saw how simpler blocks and simpler logic gates could be built up out of transistors and out of simpler logic gates. In previous video we saw the set reset latch, we saw the NAND gate, the NOR gate, the AND gate, and an inverter. Right. Combined, these can form a D latch with a clear input or reset input, same thing. So let's see how this works. First, let's start with a set reset latch. Set reset latch is basically a block, as discussed in a previous video, but in short it is a block with a low active set input, a low active reset input, an output Q, and an output Q over bar, which is always the inverse of output Q. Now in this video we will no longer need the inverted output, so we can ignore that for now. The feature or the problem with this block is that it needs two separate inputs, S over bar and R over bar, to control the output. To force the output to 0, you would need to apply a 0 at the reset input. To force the output to 1, you need to apply a 0 at the set input. Right. Pretty. Right. So in order to go from this to something that's more usable, in this case with a single D input and an enable input, we could extend it in this way. NAND gate AND gate inverter. Now to see how this works, we can write inputs S and R over bar as function of D and E. In other words, we can see, if we understand the set reset latch, we can see what happens at the set reset latch input for each state of D and E, data input and the enable input. Now, in order to do this, let's write the inputs in a truth table. Like that. And let's take a look. If input E is 0, because this is an AND gate, the output of the AND gate is always 0, the output after the inverter is always 1. In other words, if E is 0, R over bar is always 1. Right. Furthermore, the S over bar input is only 0 if both D and E are 1, because this is a NAND gate. So if D and E are 1, S over bar is 0, and in all other cases S over bar is 1. So we can write that. Furthermore, if S over bar is 0, then because this is an AND gate, this is also 0, and after the inverter, the R over bar input is 1. In other words, if S over bar is 0, R over bar is 1. S over bar is 0, then R over bar is 1. Now, because this is an AND gate, the output of the AND gate is only 1 if S over bar is 1 and enable is 1. And then the R over bar input, because of the inverter, is 0. In other words, if S over bar is 1 and E, the enable input, is 1, then the R over bar input of the set reset latch is 0. S over bar is 1, enable is 1, R over bar is 0. So that's basically the truth table of this latch, of this D latch. It doesn't have a clear input yet, but we'll get to that. So instead of simply filling in all combinations of D and E and not understanding how this works, you can also reason backwards and see what has to happen at the input in order to cause something at the output. We'll consider this the output for now then. Anyway, so if you remember how the SR-latch works, there's an output Q of all this, and only in this case when the R overbar input or the reset input is made active does the Q output change to 0, and only if the S overbar or set input is activated does the output change to 1. In all other cases the output doesn't change. I'm gonna write an X. I think that's not the official symbol for it doesn't change, but to be honest I don't remember how to do that. So there. Now you see that the output only changes here and here. So you can only set and clear the output. And you can only do that when the enable input is 1. Right? So whether the output is cleared or set depends on the value of the data input, D, in a situation where the enable input is 1. So if the enable input is 1, if the data input is 0, the output will become 0. If the enable input is 1, data input is 1, output will also become 1. In other words, the output will follow the input 0, 0, 1, 1 as long and only as the enable input is 1. That's exactly the function of the D-latch that we wanted. Now to implement a clear or reset input, remember that this inverter can be redrawn as follows. You can put a NOR gate there with a fixed 0 at the input, right? That's exactly the same. However, if you apply a 1 at that new input, because it's a NOR gate, the output will be 0 always, regardless of this input. In other words, we have a new input and we can make that input 1 to clear the latch. Now let's call that input clear. And now we almost have the D latch that we wanted. Right, this looks pretty much like that, except this clear input is high active and the reset input there is low active. Well, we can fix it pretty easily by applying an external inverter. Like that. Now it's exactly the same. Note that the inverter is not part of the D-latch in this case, because in case of the 8-bit D-latch, which consists of 8 times this block, this input is shared among the 8 1-bit latches. In other words, you only need one inverter, and that output of that inverter is connected to the clear input of all 8 blocks. So you can save 7 inverters. Right? That's how it works. So let's see in reality how that works. I took a breadboard. Let's use an elevation tool like that. Professional elevation tool. To set inputs manually and to read outputs manually, I labeled some inputs and some outputs. You have a button from left to right. You have a button to control the enable input. You have a button to control the clear input. The output of the D-latch, we'll just look at the 1-bit D-latch. The output of the D-latch is visible on the leftmost LED. The input of the D-latch can be controlled by this button. That's a D for data input, and the state of that button is also visible on the LED. So let's put this board in this test setup. Now you'll see if the enable input is not activated, the output Q on the leftmost LED does not follow the input, so the output stays off no matter what the input does. I'm toggling the input from between 0 and 1 now. If and as long as I hold the enable input, pressing that right now, the output, the leftmost LED, will follow the input, right? It will no longer do that if I release the enable input. Or, in other words, if the input has a fixed state, if the input is in a state, and you give a short pulse on the enable input, the output will copy that state, copy that input. And if you release the enable input, the output Q will remain stable no matter what happens at the input. Now the input is 0, you give a short pulse on enable input again, and the output copies that state 0 to the output and remains low or 0 no matter what the input does. Right? So I can toggle the input and control with the enable, toggle the D input and control with the enable input whether the latch copies the input D to the output or not. It doesn't copy it, copies it, doesn't copy it, copies it. And depending on the state of the input at the moment that the enable input, depending on the state of the D input at the moment that the enable input was released, the output Q is frozen, remembers a 1 or a 0, right? No matter what the output is, if you apply a high signal at the clear input, as the second button, pressing that now, the output Q is reset to 0 or low, right? And in the context of the CPU, the reset signal is system-wide, so you apply a reset signal externally and the whole system would reset to the initial state, and that's good in this case, all outputs are 0. So that's how it works basically. Now, thank you for watching, and also please watch the other videos in this series, and have a good day. Goodbye.